Perfect, thank you. So because we had that little video introduction, late last night I decided to put some fun little stats together on our wheat harvest here. So like she said, we had 365 grams of clean seed, which is approximately 0.8 pounds. Now we had 90 participants yesterday, so at a minute each, that was about 90 full minutes of threshing time that we did by hand. So one person, if we were to come up with a rate, could harvest 0.009 pounds per minute of wheat. So now if we go and we look at, say, an irrigated crop, 80 bushels per acre yield on 160 acres, that means we're thinking about 12,800 bushels of wheat. And at 60 pounds a bushel, that's 768,000 pounds. I hope I got all the division and multiplication right here. So if we divide that by our threshing rate by hand, I figure it would take one person 162 years to do that quarter section by themselves, or even with a whole lot of us yesterday, about 2 years to do. So I thought that's pretty amazing what a combine can do in 6 or 7 hours, right? So I'm here to talk to you today about rapid fire research. And I knew I was following Dwayne Beck, which was going to be a really tough act to follow. So, you know, he's the Oscar winner. He's got all the insight and the depth into what's going on. And because I'm doing rapid fire research, I figured I'd go after the cheap thrills here and maybe set my own world record for the most explosions in an agronomy presentation. I'm pretty sure that one doesn't exist. So I'm going to talk to you about a number of different projects that we're working on and collaborating on today. Deep banding of immobile nutrients, cover crop projects, using crop sequencing and rotation for fusarium head blight managing and risk modeling, and then a novel crops program that we're working on to help integrate novel crops into rotations here, and some little extra tidbits on our precision canola project that we're working on getting wrapped up for the springtime. All right, second one. So when it comes to integrating new crops into rotation, there's a lot of things that go into how you integrate that crop. So with something like quinoa here, everybody's really interested in it, but our first year was a bust. We didn't get any of this nice seed that we did this year. There's limited herbicide options, rotational challenges. There's challenges with straw and residue management, and insects and diseases and things that we might not necessarily know about. So we usually have a basics on you know, maybe how to plant it, a seeding rate and things like that, but there's a lot more challenges to growing a crop, especially when you don't know really where it fits into your rotation. So what this first project is aimed at doing is integrating these new crops into a system that we already have. So, you know, just like hemp here, we're limited with herbicides. We've got basically edge we can put down in the springtime, and then a sure for grassy weeds in crops. So what this project did was we've got 9 different crops here, and we've kind of intersecting 2 different projects. So we've got everything in big blocks just to maximize space, because these are the biggest really big plots. Like they're bigger than any of the small plots we're used to doing. So we've got durum, dry bean, hemp, quinoa, and corn are kind of our specialty crops, and then peas, canola, barley, and wheat kind of our traditional crops. So this is just the first year, so we planted everything as we would, and we're managing them just like we're thinking we want to. And so we've got a first set of yields. We've got durum, barley, and wheat and corn with pretty high yields. Our quinoa was relatively low yielding, but we did get good seed this year. And we're running this all under irrigation. We're trying to maximize the yields, and we're also using this for another purpose here. So what we're going to do is year one, we've got these big blocks, and we're just setting up the precursor crops. But then we're going to come in next year, and we're going to seed across everything again. So what's going to happen is we're going to end up with a giant matrix of every permutation and combination possible. So we'll have durum on wheat, and every combination. So in this case, we'll have 81 different combinations of before and after crops. And that's going to give us a huge, robust data set for figuring out the best place to integrate these things. So that's part one, and that's going to be, that's led by Dr. Jan Slasky. And part two is looking at the leaf disease and the fusarium head blight within these, within the cereals crops. So what we're doing is we're also going to look at whether or not these precursor crops can affect the levels of fusarium head blight. So the third year, what we're going to do is if we have enough disease pressure, we'll go back in and we're going to see the entire area to durum and then have a whole bunch of little small plots with those two precursor crops ahead of time. And this section is led by Dr. Randy Kuchar out of the University of Saskatchewan. So current management practices for fusarium head blight is using non-host crops in the rotation. It's using resistant cultivars, fungicides where applicable. And right now what this project is going to do is it's going to look at a crop management and risk management tool. And that's where all the data is going to go for this. So moving on, another new project we're part of is this deep banding of immobile nutrients. And this is led by the guys up in Sarda. So one of the big things we're doing here is we're doing lots of soil sampling. Why are we soil sampling when it comes to deep banding of immobile nutrients? Well, we've got really excess nitrogen in our soil in this location here, but nitrogen is a mobile nutrient. So you look at the nitrogen cycle and it's just a big tangled web of different places that your nitrates and nitrates, evapotranspiration. Nitrogen can move around in a lot of different ways. But a lot of our other micro and macronutrients don't move around in the soil as much. So, you know, if you think of copper and you take a penny and you bury it an inch under the soil and you flag it and you come back 10 years later, a penny's still sitting there. And so is a copper. So mobile nutrients get bound up to different things in the soil, different particles and organic matter depending on their form. And so, I'll just skip ahead here. So what we did was we took some soil samples and we got a really obvious stratification. And so after years and years of shallow banding all of our nutrients in a no-till system, we end up with a really stratification of all those immobile nutrients up at the top 3 inches. So you can see this pretty clearly in our soil sampling that we did 0 to 3, 3 to 6, and then our deeper depths. So down on the phosphorus, Lethbridge is a site that tends to be really deficient in phosphorus. Potassium, they tend to be quite deficient in the Vegreville type area. Sarda is deficient in the sulfur, and then Vegreville and Sarda a little more so on the copper end. So here's a little graphic, I guess, to show you the stratification. So you can imagine if you're zero tilling, all your immobile nutrients just end up in that layer up at the top above the red band. And so, you know, listening to Dwayne Beck, I guess we're kind of treating a symptom here maybe, but what we're going to do and attempt to do is to deep band those immobile nutrients further down into the soil and hopefully give them better access to the root zone that way. So what we did was we took our hoe drill type opener, we measured everything up to match up with our current disc drill setup, and then we went down to about 5-6 inches down and pre-applied all of our immobile nutrients in a deep banding treatment. So I got a quick little video here to show you what that looks like.
This is start date equivalent, May 19th, 2018. Mike Gretzinger reporting live from the Farming Smarter
We're having fun.
site, Lethbridge, Alberta, Canada, the world. Here, deep banding. We've got phosphorus, potassium, sulfur. Down in the soil, 5 to 6 inches. Perfection.
So you can see we're banding down pretty good. It's technically like a cultivation type
Start
treatment. All right, so So what we're up to is when that's finished, we get this nice little randomized section across the trial. So we're seeding peas, wheat, and canola, and we're doing it on a 3-year rotation. So we're going to come back every year and seed the wheat on the peas, canola on the wheat, and we're going to have this in the same site for 3 years. So our first set of treatments is that shallow banding. This is what we're used to doing. There's no deep banding treatment or any cultivation in this treatment. We've got one-time copper, potassium, phosphorus, and then a one-time of all 3 nutrients. And then we've got that deep banding treatment. So what we did for the deep banding is we did a 3x rate. So that's the only time we're going to deep band, and that's the only time we're going to use that piece of machinery. So the rest of the years will be no-till again following that. And then we've got a control treatment where we didn't do anything. We're not going to put fertilizer. We're just going to put the seed down. And so we do have 1-year results. This is just one site year in Lethbridge this year, but we saw some interesting things. Now, this year in May, we got really hot pretty early on. We had some crusting and some seeding issues. And the deep banding treatments where we went in and cultivated, I think we just got better seed to soil contact, and we had better access to moisture when that seed was germinating. And you can see where we're deficient in phosphorus and where we did the 3x phosphorus, potassium, and copper rates, we had a little bit of a yield bump there, and it was significant compared to some of the other treatments. And then we saw the same thing again in the wheat. And I couldn't find a good picture of this, but you could see it when you walked out in the field. We were stressed a bit for drought, but you could see the nutrient treatments side by side and pick them out as you walk through the reps. The peas didn't yield well, so I'll skip that over. So stay tuned for more on that one. The next project I'm going to talk about is a cover cropping project. So we've heard a lot about this week a little bit. So this one is led by Dr. Yvonne Lawley out of the University of Manitoba. So let's start with this. Why cover crop? Cover crops are something used for soil erosion, fertility, quality, water retention, water management, weed management, pest management, diseases, all sorts of things can go into why we would cover crop. A little definitions for you. So intercropping is like the piola that Kelly Turkington talked about the other day. Double cropping would be doing something like winter wheat and then growing soybean after it right away and kind of doubling up and getting two harvests in 1 year. Relay cropping is a really similar thing. That's where you're just going in and broadcasting that second crop before harvest. And then cover cropping is kind of similar, that we're just trying to keep that bridge going and have something on there over the winter when we normally just have straw. So for this trial, what we did is we have wheat, canola, durum, and peas. And it's called a fully phased trial, so that means we also got canola, durum, peas, and wheat. And durum, peas, wheat, and canola, and peas and wheat, and canola, and durum. So we've got them in every possible combination every year, just to make sure starting on one versus another doesn't have a different outcome. We've got wheat, canola, and canola, wheat. And then we've got a perennial alfalfa crop. And so for each one of these, they're going to be looking at them with and without a cover crop. So for the wheat, we chose like a clover mix. For canola, we put lentils. For durum, we put driller radish. And for peas, we did a fall rye and winter wheat as our cover crops. So we got pretty good yields. All these colored bars should be the same because we haven't had any treatment differences yet. We haven't had a cover crop. The deviation's a little bit high, but everything looks good so far. The big challenge is we only had half of our long-term average in rainfall this year. And so that means establishing cover crops is hard to do and it's difficult. And potentially cover crops may actually end up being detrimental to our system. So we're going to have to look forward in the next couple of years and see what happens. So this is, just a picture of our perennial alfalfa. This was the first cut that we got, and this was in October. So it was a tough go on those cover crops. All right, next up is our precision canola. So we've had a lot of interest in this project. I got more phone calls on this than probably any other project that we've done combined. So the idea behind this project was that these planters are out there, and producers are using them in row crop situations for corn and soybeans and other crops, and they want to know how adaptable are they for other small grains. And so a little bit about a planter. If you don't know the difference between this and an air drill, the seed's metered out using a little sprocket or something like that. It falls down into a tube, a fan blows, and the seed just randomly blows through the tube until it falls out the opener. The difference in a planter like this is you've got a pretty specific set of sprockets to match the seeding rate, and a plate system right in here. And this is where the magic happens. So there's vacuum pressure that pulls the seed onto these plates. And then as it rotates and goes out the bottom piece, the seed just drops down due to gravity. The vacuum pressure is no longer there, and you get really uniform spacing of all your seed as opposed to a random distribution like you'd get in an air drill. This is just kind of showing some of the things that could go wrong. You could have gaps, spaces, doubles, or a quad. So this is our seeding rate trial. So this is just an aerial shot giving you a good description of what we did. So we have the treatment with the air drill at 9.5-inch spacing, and this is our standard air drill with pillar laser openers that we've been using for the past 10 years. We've got our monosem, which is that precision planter, and we've set it at 12 inches. That's a really narrow row spacing. It's pretty impractical in the real world, but we wanted to know, on a narrow row, how much better is it going to be, if any. And then we've got a wider row setting, which is a little more common, so that's the monosem at 20 inches. And we've got 5 different seeding rates. 20 seeds per meter squared is under a pound an acre, basically. 40, 60, 80, and then just to keep the distribution geometric, we went to 160, which is way higher, I'm sure, than anybody's seeding. And this, I got one more here. So this UAV shot kind of sums up what we're seeing really well. So if you look at the very bottom left corner, the air drill at 20 seeds per meter squared, you've got a lot of big spaces in there. And if you look at even at 20 seeds per meter squared, that monosem on 12-inch spacing is really uniform. You have hardly any ground cover showing. If you go to the 20 inches, you can see a lot more ground cover just because those rows are wider. The rows themselves look nice and uniform, but we may not be optimizing things, and I'll get into that here really shortly. So this is 9 site years now of data. This is average yields by seeding rate in Lethbridge and Medicine Hat. And I separated into dryland and irrigated because we have such a big yield difference, and because we saw some different things in under the different management systems. So the first thing you'll notice is we've got a pretty linear response to yield when it comes to seeding rate. So as our seeding rate increased, we saw that our yield increased. So if you look at the air drill at 9.5-inch spacing under irrigation there in red, it goes up from about 65 to 75 bushels per acre. If you look at the air drill on rain fed, it goes from about 35 to 45 pounds an acre. And we saw a kind of similar thing with the precision planter on 12-inch spacing. But where things got interesting, on irrigation, the precision planter at 20 inches actually kind of dropped back off at the high seeding rate. And that's likely, not necessarily real. It probably flattens out more than anything. And that's just due to self-thinning, and there's only so many seeds you can plant in a wide row. The wider your row, the higher the concentration of everything that goes into those rows. And so there's just a maximum that's going to work in there. And then on the 20 inches in the rain-fed site, we saw the same thing, kind of a plateau. And our most interesting and coolest result that we've got here is that in irrigation, our precision planter at 12-inch spacing actually had the highest average yield at about 40 seeds per meter squared. That's like a pound and a half an acre. And that's kind of the stories that we heard coming into this project, and it's really neat to see it happen. Now risk-wise, we haven't delved into that and kind of stuff that Murray Hartman does with the risk management tool. So I'm absolutely not recommending to seed 20 or 40 pounds an acre just because you've got a narrow row spacing on your precision planter. But if you look at it, even at the 20 pounds an acre, that's still our best yield under irrigation compared to any of the air drill treatments and any of the precision planter treatments. So that's really cool to see, and we're going to keep building this report and integrate the emergence counts and some more of the UAV information and stuff like that, and kind of build a more comprehensive insights into that project. So these are just some shots of some of the things that happen, so you can really see the maturity differences going from 20 to 160 seeds per meter squared. And then, like I said, we had some challenges in the dryland site seeding this year. We made some adaptations to the air drill thinking it was going to be beneficial, and because of the weather, we actually had some challenges, and so we had some split emergence there. So what are we getting at with this seeding rate? Well, the air drill on the left, this is stole this slide from Lewis, but the air drill on the left, that's showing that picture before and the random distribution of seed. And there's big gaps and there's spots where there's lots of seeds close together. And so you get some big branching plants of canola and then some little spots where there's lots of little tiny ones with no secondary branches. So what's that monosem at 12-inch spacing doing? Well, it's just making everything really nice and crisp, and it's getting really kind of good spatial distribution of that seed within the field. So everything's nice and uniform. You got really even emergence. We saw increases in emergence with monosem on 12-inch spacing. And the challenge when you move to that 20-inch spacing is that, like I said, you're concentrating everything in those rows. And so you may have good distribution from row to row, but within that row, everything gets a little bit tight and you're not maximizing space. So I think there's maybe a sweet spot in between. We couldn't test every size, but maybe 15 inches isn't a bad compromise here going forward. I thought this was pretty clever of Lewis. So this is our future prime placement. So maybe if we can adapt that precision planter to get a perfect geometric distribution, I mean, this is maybe ideal seed placement within the field. Oh, all right, so that's part one of the precision planter project, but part two was looking at seedling safety. So when we're putting phosphorus down and we're widening our bands, like I said, we're really concentrating everything that goes into there. So if we're going to do seed place phosphorus, we know there's some potential safety issues, so we wanted to know what that is. So we did the same three treatments. We've got the air drill on the left, the planter at 12-inch in the middle, and the planter at 20 inches on the right. And then we did 0.5, 10, 20, 40, and we didn't get any damage really the first year, so we upped it, and we did the max that our unit would allow us to do, and that was 60 kgs per hectare of phos. So here's showing you some phos deficiency. Like I said, our soils are pretty deficient in phosphorus. And I broke these ones up into one slide for dryland, one slide for canola. So this is a really cool result here. This is our air drill at 9.5-inch spacing in the red on the left. And we saw a pretty flat line. I mean, phosphorus maybe helped in some cases, but this is the average of, I think it should be actually 9 site years. Oh no, it's just dryland, so 6 site years. It's pretty flat line, and then we see when we get to 60 pounds an acre, it dips down. And you see the same thing with the precision planter at 12 inches, and you see the same thing at 20 inches. So on average, that 60 kg a hectare, that's where things kind of went south for us in terms of yield. Would I recommend going that far? Probably not, but when we started, we were told maybe 5 max might be the safe rate, so I think we're maybe safe to go a bit higher, but we'll have to see what the published data and the other literature might say. And so I kept this separate because the irrigated result's really interesting as well. So irrigation, we didn't see the same thing. So this is the dry land, everything dropped off at 60. In our irrigation, we kind of got this weird response. On the air drill, it dipped down. I'm not sure if that's real or what's going on. We got to dig into it a bit more, but actually went back up as it got closer to 60 pounds per acre. And our precision planter at 12-inch spacing, it actually got better as we went to 40 and 60 pounds per acre of phos. So kind of a strange result there, and we'll see how real those turn out to be. So I kind of had this crazy idea of tabulating all that in a different way to kind of visualize it differently. And so this is kind of a hybrid of like a medal count and a Sudoku puzzle. And so our seeding rate results, if you want to think about it this way, 7 times our precision planter with 12-inch spacing had the highest average seeding rate. 2 times it was only second best. Twice there was 2 site years out of 9 where our air drill actually did better depending on the environmental conditions or what was happening. And every single time our precision planter at 20 inches spacing had the lowest average yield. And we didn't expect to find that. And I think that's kind of interesting. So that's why I said, you know, maybe if producers are looking at doing this, maybe consider the system, dryland irrigated, and maybe consider that slightly narrower spacing may be key. And then the exact same results happened for the liquid phos. So we never had the best yields with our liquid phos on 20-inch spacing with a planter, and most of the time we had it at 12-inch spacing. So we got a couple other irons in the fire, using that planter to do some precision pulse work, maybe some precision durum, and then potentially some other field scale trials. This is a shot I took the other day. This is all the different places we're trying to pick our projects to go. So we've got some more extension stuff, a pilot project with the EM38, some work on field scale neonics and some kochia, doing some innovative VR and 360 work and some biobed stuff, some canola modeling, shelter belts, and pollinators. So we've got a lot of things going on, and hopefully some really interesting projects coming up for you in the next couple of years. That's it. Here's my record.
Yes, that was definitely mind-blowing. Does anyone have a quick question for Mike? I know that you will be around until the very end, and we are up on a coffee break, so maybe I'll let you go, Mike, and then if people have questions, they can give you a call. So one more hand for Mike Gretzinger.